All right, now remember this video, even though it's on Edpuzzle, you can skip through it. I turned that feature on so that you could skip ahead to where we left off in class, but I'm going to start from the beginning here in case you need to see something else again. So this is the last coordinate system that we're doing, called the spherical coordinate system. And so this is mostly useful, obviously, when you're using spheres and cones. And so the equations and things that you use for this is just it just makes things easier when you're using those two types of things. So some basic equations that we have here. First of all, a sphere. So you guys know that a sphere is going to be, usually it's x squared plus y squared plus z squared equals r squared. But in this case, a sphere is going to be just rho equals, so rho equals a number, like say 3. So remember that's the, it looks like a P kind of, it's R-H-O. It's rho, that's the Greek letter rho. And then this number over here, that's going to be the radius. Okay, so if you have something that says rho equals 3, then you have a sphere of radius 3. And so if you need to, you can also put that back in rectangular form as well. Here is the half plane that we discussed back when last section as well. So for example, we could see something like theta equals pi over 6. So that is a half plane. It would be 30 degrees from the x-axis. So like if it were this picture right here, this would be 30 degrees right there. And it's coming out of the z-axis. It's only going halfway out the one side. All right, and then you have cones here. So this is something pretty much new, just like the rho was. And this is going to be a new variable called phi. So usually you've seen theta before. So theta is a circle with a line across. This one, you kind of like draw an O and you come back down through. So that's phi. Right? And if you have, like, say, phi equals, let's say, pi over 4. So pi over 4 is going to be the angle down from the z-axis. So that angle right there is phi, and so when somebody tells you phi is pi over 4, that means you have a cone with a 45-degree angle for the sides right here. Okay? And so if somebody told you that it was past 90, then what would happen is your cone would kind of flip over. So for example, let's say phi was equal to 2 pi over 3. And usually you're using radians when you do this, so 2 pi over 3 would put you past 90, so it'd be 120 degrees right here, right? And so that would turn your cone and basically would let you know that you have, 60 degrees left right there, so however you like to think of it. So it's basically the angle off of the positive z-axis. All right, so here are your conversion equations for spherical coordinates. So there is your sphere down here. All right, and if you have an x in rectangular coordinates, you want to change it to spherical coordinates, you use rho sine phi cosine theta. So make sure that distinction is there with the two different variables right there. And if you want to replace y or z, there they are. All right, so in this coordinate system, the simplest solid is a spherical block determined by how far you go out in a sphere. So your rho is going to be how big of a sphere you have. Your phi, or your theta, is going to be, how far you go around. Okay, so this is how big of a sphere you're at. And your phi is going to be how much you are down from the z-axis, right? So if you have the x, y, z-axis right there. Okay. All right, so a quick example. So you can do, you can evaluate a triple integral in spherical coordinates provided that the solid shape region is simple with respect to one of the 6 possible orders of integration. So remember that when you do this, you're going to have d phi, d rho, d theta. Those are going to be your 3 pieces right there. So let's do an example of if you have a sphere with a cone cut out of it. So you have a sphere of radius 4. And you have a cone at pi over 4, all right? So look what would happen right here. Oops, I put the wrong thing here. This is supposed to be a phi, not a theta. It's supposed to say phi equals pi over 4. Sorry about that. All right, so when you do this, you would have your sphere, right? The radius of that thing would be 4, and it's centered right on the XYZ axis. And then what's happening is you have this cone coming down at 45 degrees, all right? And this is saying the volume of a sphere with the cone cut out. So you basically don't want this part, but you do want all the pieces on the outside. So that's what we're going to try and write a little triple integral for that. Okay, this little part right there. All right, so here we go. So when I write a triple integral for that, we're always going to go d rho, d phi, d theta, right? And you can switch it around if you need to, but my rho. So if I am going to go out from the center to the sphere, so 0 to 4, my phi, so remember now this is going to be a little bit different here. I'm trying to go from here to there. So my phi right here is at pi over 4, and my phi all the way at the bottom is pi over 2. So remember, you always want to put your lowest to your highest. Not pi over 2, sorry about that, pi. You probably thought I was crazy. All right, and so then those are going to be your boundaries on the second part. So pi over 4 to pi. And then the last piece, you're going to do theta, which is your distance around. So that would be 0 to 2 pi in this case. Now I'll explain on the next page, just like we did with cylindrical coordinates, where you had to put an extra r when you did your dr and d theta. Well, for spherical coordinates, you have to put this, rho squared sine phi. So if you're trying to do the volume of something, you do have a 1 right here, but this always has to be there. That you'll learn in our next section is called the Jacobian. It's for when you're going back and forth between different coordinate systems. You have to put something, sometimes you have to put an item there that kind of is like the rate of change in a way, like the it accounts for the difference in the systems, and you'll see that in the next section a little bit. But anyway, you always have to put that. All right. So just like with cylindrical coordinates, you can visualize a particular order of integration by viewing the iterated integral in terms of 3 sweeping motions. All right, so this row right here, remember we're going to go from basically the center out to a certain sphere. Then phi is going to take you down to a certain angle, and then theta takes you a sweeping motion around however far you need to go. So that's what these 3 pictures are. And right there's that thing, that piece that you have to put right there in every problem. Okay, so this is just a picture of everything going on. And when you do a triple integral in spherical coordinates, this is just another explanation of how you have to put the rho squared sine phi. All right, you always have to put this, just like you did with cylindrical coordinates. You had to put r, dr, d theta. Okay, and so just know that. All right. So here in example 1, we're going to just draw a little picture. A sketch a solid described by these inequalities. So when somebody tells you rho is between 2 and 3 and equal to 2 and 3, and staying in between there's those numbers and equal to, remember that is just a sphere, and it's between a radius of 2 and a radius of 3. So basically, if I try to draw that, I would have, like, if I was thinking of like a melon or something like that, it would be like the rind of the melon, like the inside was scooped out, right? So I would have a radius of 2 and a radius of 3. So I'd have one sphere, and then I'd have another sphere. And I guess I could try and draw those across there. And it's going to be pretty hard to visualize, but maybe you can kind of see. So it's going to be the space between those 2 things, between something with radius 2 and radius sphere 3. So imagine something with like a thick skin, right? So like the skin part between those 2 spheres, like if you had a basketball with like a really thick skin. All right, and then it says phi is between pi over 2 and pi. So phi being between pi over 2 and pi means that you're basically going to have a cone that is between pi over 2 and pi. Well, pi over 2 puts you to right here, and here's the negative z-axis, and pi puts you further to there. So it's going to be between here and here. And so it's going to be basically the bottom part of this, right? And it doesn't describe anything to do with theta, so we're going to consider it all the way around. And so basically what we're doing here is we are going to have the bottom half that's below the xy plane. And so if I kind of try to draw this shape a little bit, I have my bottom half of my sphere, and it's going to, if you could imagine that that was like a bowl or like a cup or whatever, and you know the inside is there, and you are basically figuring out the volume of this portion right inside here, the bottom half, right? So it's like a cup or a bowl, however you want to think of it. Okay, below the xy plane. So if you're drawing, your drawing and your explanation should be able to cover it. Okay? All right. So for this next example here, we're actually going to go ahead and evaluate some integrals for examples 2 through 4. You want to evaluate this integral, but remember we have to change everything over to spherical coordinates. So right away I notice x squared plus y squared plus z squared. Remember that's equal to rho squared. Okay, so remember when we do our triple integral, I'm going to have to put rho squared there. But remember you always add your own rho squared sine phi. And then we're just always going to put d rho, d phi, d theta. All right, and there's going to be an easy way to evaluate these integrals in most cases. So let me go on with that. So we want to evaluate this integral over B is the unit ball. So we want this, the region that we're integrating this over is a ball, and it has a radius of 1, right? A sphere with radius 1. So my rho, I'm going to go from 0 to 1 because I'm staying inside that ball right there. If I want to do the whole ball, so the area or the space that we're evaluating this over is a ball, right? So I have to consider that I want to go the whole way. I want to go all the way from the top to the bottom of that thing. So I'm going to go, my phi is going to be 0 to pi, and I want to go all the way around. So that's 0 to 2 pi. Okay. All right. So now you notice that every single one of these numbers on our integral, the bounds of our integrals, they're all numbers, right? Everything up top, they're all just numbers I'm evaluating these things for. And so that's going to make things very easy for me, because if they're all numbers, then I can go ahead and separate this into 3 different integrals and just multiply them together. I don't have to treat it as like an integral that I have to keep like doing, the inside integral, then the next one, then the next one. What I can do is I can separate them 0 to 2 pi. Remember that was my theta. Times I can do 0 to pi. Remember that was my phi. And then I can do 0 to 1. That was my rho. And with those, I will put the correct variables, or the ones that go with them. So this one on the end, d rho, remember I had rho squared, so rho, not squared, but to the 4th, because I had squared twice. All right, and then phi, I had a sine. All right, and then for the theta, I have nothing involving theta here, so I'll just put a 1. All right, so when we do this, remember if I'm integrating with respect to 1, I'm just going to get theta evaluated from 0 to 2 pi. So that just puts me at 2 pi for that piece, times integral of sine is negative cosine, right? So I get negative cosine phi, from 0 to pi. So let's see, negative and cosine at pi is negative 1, minus cosine at 0 is 1. So it'd be negative 2. So that puts me at negative 2, which is positive 2. Okay. And then for the last part, I have the integral of rho to the 4th, which is rho to the 5th over 5, evaluated from 0 to 1. So I just get 1/5 from that. So when I'm done, I can simply just do 2 pi times 2 times 1/5. So I get 4 pi over 5. And that will be the easiest thing that you can do. You can't always do that, but if there's 3 numbers up here, if they're all numbers for your evaluation pieces, for your bounds of your integral, then you can separate it, and that's going to be the easiest way to do these. All right, so here, find the volume of the solid region that lies above the cone this time, so not like that first example. So above the cone, and this cone right here, that's just our 45-degree angle cone. That's our basic cone right there. And so I know that my phi is pi over 4. Okay. And I have the sphere of radius 3, so I'm going to have rho equals 3. Okay. All right, so, and we're doing volume. So here we go. So I have 0 to 2 pi. I guess I should write them all first. Sorry about that. So I have, remember, d rho, d phi, d theta. And 0 to 2 pi for my theta. I'm doing inside the cone, so my phi is going to go from 0 to pi over 4. Because remember, I want to keep this area right here, between there. And my rho is going from 0 to 3. And I just have rho squared sine phi. Okay, I want to set that one up. I mean, the answer is pretty much, just like we did before. I'll go ahead and evaluate it out, but it's going to be pretty simple. So anyway, we're going to have 0 to 2 pi, and we have no theta here, so that's going to be d theta times 0 to pi over 4. For my phi, I have sine phi and d phi. And then I have rho squared, 0 to 3, and I have d rho. Okay, all right, so this one, like we saw earlier, is going to get us 2 pi. Over here, I'm going to get rho to the 3rd over 3 from 0 to 3. So it'll be 27 over 3, which would be 9. Okay, so this middle one's going to take a little bit more work, but integral of sine is going to be negative cosine. And from 0 to pi over 4. All right, so negative and cosine of pi over 4 is radical 2 over 2, minus cosine of 0 is 1. And so basically, we're multiplying these 3 things together. So my 9 and my 2 pi, so 18 pi in front, so I'll get negative 18 pi. And I have radical 2 over 2 minus 1 there. And you can change that or multiply it through however you like. I mean, if you wanted to multiply it through, you could say that your answer is, let's see, negative 9 pi radical 2 plus 18 pi. I mean, if you really wanted to like multiply it out. So however you like to do it. I feel like I made a sign error there. Let's make sure. All right, we're good. All right, sorry about that. I just wanted to make sure I was doing okay there. All right, so example 4 here. We have this integral that we're trying to do. So remember, when you have numbers right here, or when you have variables right there, that's basically kind of acting as your density in a way, if you want to think of it, because once it gets past 3 dimensions, it's kind of hard for us to think of it geometrically. But we want to stay between the spheres 2 and 4, and above the cone at phi equals pi over 3. All right, so when I set this up, we're going to add our own, leave a little space here, rho squared sine phi, remember? All right, and I have d rho, d phi d theta. All right, so that x, y, z right there, remember, we have some things to put in place of that. So back here, remember, x, y, and z are my three equations there. So if I multiply those together, let's go ahead and do that while we're here. I'll have rho to the third, because x times y times z, I'm going to get a rho to the third. I'll get a sine squared phi. I'm trying to just collect everything that I see right here. Sine squared phi, I'll have a cosine phi, and I'll have a cosine theta and a sine theta. So I got, theta. I got a lot going on right there. All right, so we'll collect those back on another page, but just so you understand when I write them, that's where they're coming from. All right, so I already had a rho to the third, so I have this rho squared, so here we go. So rho to the third, and I have a sine to the third phi. Oops, sine squared, because on my paper I have it added in there. Sine squared phi. I have a cosine phi. And I have a sine theta and a cosine theta. So sine theta, cosine theta. Okay? And I'll put it all together in the end. All right, so I got my triple integral. I got rho to the fifth. I have a sine to the third phi, because I got 2 here and 1 there. I get a cosine phi. I have a sine theta and a cosine theta. So this is going to be a little bit more complicated than before. And then we have d rho, d phi, d theta. But I am going from between the two spheres, 2 to 4. And I am going from 0 to pi over 3 above the cone, 0 to pi over 3, and then all the way around. So this is separable. Okay, so let's separate it. So for my rho, or actually let's do theta on the outside, I got 0 to 2 pi. And if I have my theta, so everything with theta is my sine and my cosine, right? So sine theta, cosine theta, d theta. And then my d phi, so my phis are sine to the third phi, cosine phi, d phi, and then 0 to pi over 3. And then for the last part right here, I have rho, so 2 to 4. I have rho to the fifth, and then d rho. All these new variables, hard to remember. All right, now, so this one right here, I would get, obviously, rho to the sixth over 6. I would evaluate that from 2 to 4. But something's going to happen to this, so I'm just not going to do that for right now. Here, I would want to make my u be sine phi, so that du would be cosine phi. So if I had to integrate that, I'd really be integrating the integral of u to the third du. Okay, and then you would go on and do that. This one over here, though, I could make my u sine or cosine. I'm just going to make my u into my sine theta, and du would then be cosine theta, d theta. I don't have to worry about any kind of like negatives and positives. All right, and so I'm integrating u du. When I do that, I get u squared over 2. So remember, u was really just sine, so I get sine squared theta over 2. Evaluating from 0 to 2 pi. All right, now 2 pi and 0, sine is 0 at both of those places. So what's going to happen is this whole integral, this whole triple integral is just going to go to 0, because this part comes to 0. So once I know that's 0, doesn't matter what I multiply it by, 0 times the next thing times the next thing, it all just comes out to 0. So that is annoying, but at least we know now. We didn't like work it all the way out. So if one part comes to 0 and you're multiplying it by the others, then the whole thing's 0. And that might not make much sense geometrically, but what's happening there, we're not doing the volume, remember, we're doing this integral here, and what happened, that happened to us because of this piece right here. It just made that happen. All right, so next one. Set up a triple integral here to find the volume of a solid that lies above this cone and below that sphere. Now, this sphere is a little bit different from the others that we've done. So remember, rho equals 16 cosine phi. So that sphere, let's look a little bit of what that means. All right. So what that means right here, remember that if we wanted to change it back right here, so let's look back at some of these equations that we had before. Okay, so especially this one for I need a rho squared to like turn something into a sphere. So I'm going to do a little bit of shenanigans here just to fix this up a little bit. So I'm going to multiply both sides of my equation. My rho equals 16 cosine phi. I'm going to multiply both sides by another rho so I can get a rho squared on the left-hand side. And then I'm going to be using this equation as well. All right, so just bear with me for a second. All right, so this guy right here. So I'm going to multiply both sides or everything by a rho. All right, so I'm going to get rho squared equals 16 rho cosine phi. So I'm trying to change this back to rectangular coordinates. So remember, just to make you understand what it looks like. So rho squared is really x squared plus y squared plus z squared. And over here, notice that this is z now, right? So I have 16z. Okay. So if I were going to turn this into like a regular sphere like we're used to seeing the equation, it goes like this. X squared plus y squared plus z squared minus 16z equals 0. I'm going to complete the square on this piece right here. So half of 16 is 8. 8 squared is 64. So I'm going to add 64 to both sides. So just bear with me. I'm just changing how it looks. So I have x squared plus y squared plus, and then this part turns into z minus 8 squared equals 64. So to explain to you what this sphere is, that's why I changed it here. Look at what this sphere is. This sphere has a center of 0, 0, 8. So it's up here at 8. It also has a radius of 8. So the sphere is up here. Okay, and it's coming around. All right, going like that. Okay, and then it has the cone at pi over 6. So that cone is cutting through right here. Okay, so a triple integral to find the volume of the solid that lies above the cone and below the sphere. So we're basically doing the volume of the stuff inside here. But I just wanted you to realize like what the picture was and what this kind of equation, like what it's going to do to you, or what it does. Okay. All right. So here we go. So I have a triple integral. So I'm doing the volume, so I'm going to put a 1 right here, but remember, we're always going to put our rho squared sine phi. I have d rho, d phi, d theta. All right. So when I'm doing my rho, I am going from the center from 0 all the way up to this circle right here, right? Because I'm not going out to the circle that way, because the sphere, but I'm going from 0 up to the circle. All right, now I'm only going to stay within that within that cone, but basically I could say I'm going to here, but eventually I'm going to block myself off to stay on this cone right there. So I'm going from 0 out to the outer edge of my sphere. Okay, so when I say that, I'm going to go from 0 and I'm going to put 16 cosine phi right here, because that's what I want to stay inside. So 0, 16 cosine phi. All right, and then I want to stay within the cone, 0 to pi over 6. And I want to go all the way around, so 0 to 2 pi. Now, this one right now is not separable. Do you notice that the first integral and the innermost integral has 16 cosine phi? Once I get rid of that, I can separate this integral. So we need to do that. All right, so here we go. So I have to integrate that, or I might be able to. Let's see, just see how it goes. So integrate this with respect to row. Okay, so I'm going to get rho to the third over 3. Sine phi is just sitting there. I have to evaluate this from 0 to 16 cosine phi. I still have d phi to do and d theta. I still have 2 integrals left to do, 0 to pi over 6 and 0 to 2 pi. All right, so let's figure out this part right here. So I'm going to plug in, when I plug in 0, that'll go away, but when I plug in 16 cosine phi into rho to the third, so I basically get 16 cosine phi all to the third over 3 minus nothing, and then times sine phi. Okay, and then I still have d phi, I still have d theta, I still have my other 2 integrals here. All right, so now if I would like, I could separate this out. So I think that I will. The outermost integral is 0 to 2 pi d theta. Nothing here has to do with theta, so it's going to be a 1 times. I have 0 to pi over 6, and I have, let's see if I can take some of this out. I have 16 to the third over 3, and then I have cosine to the third phi sine phi, d phi. Okay, all right, so this part's definitely going to give me 2 pi, so that'll be not too hard. Over here, I got my 16 to the third over 3, just waiting here. This piece here, I will make u be equal to cosine theta, or phi, sorry, and that way my du will be negative sine phi, d phi. So when I integrate that, I'm basically integrating u to the third du, but remember I have to put a negative in there. So I get negative u to the fourth over 4, and my u is really cosine phi, so I get negative cosine to the fourth of phi over 4. All right, so from pi over 6 to 0. So let's take that negative out of there, and why don't we also take the 4 out off of there. So I'm going to have a 1/4, a negative. And cosine of pi over 6. Cosine of pi over 6 is radical 3 over 2, but it's to the 4th power. All right, so radical 3 over 2 to the 4th power, that would be, the bottom would become 16, and the top would become 9. So it'll be 9/16, minus when I put 0 in. Well, when I put 0 in, I get 1. All right, so this is what I'm going to put with my other piece right here. All right, so let's see. We got 2 pi times 16 to the third over 3 times negative 1/4. Then I have 9/16 minus 1. So 9/16 minus 16/16 would be negative 7/16, right? All right, so let's clean this up even more. I got 2 pi, 16 to the third over 3, and 2 negatives makes it positive, so I have 7 over 4 times 16 is 64. All right, and I'm sure this could be cleaned up anymore. 16 goes into 64, but that's, and all that, basically what you're going to get when you clean this up, you get 896 pi over 3. Okay, all right, probably used a calculator on that. All right, so now approaching the last part right here. So try not to go too fast for us here. So sometimes we have to change things from rectangular to cylindrical or spherical. So here we go. So we're going to change this first one, example 7. We're going to change it to cylindrical coordinates. So this isn't really this section, it's from before, but just to practice that again. Okay, so remember cylindrical coordinates is our, we're going to be using like dr and d theta and all that kind of stuff, okay? All right, so first of all, we have to understand what we are staying between. All right, so what this is telling us to do is we are staying from, remember this is z equals x squared plus y squared to z equals square root of x squared plus y squared. So z equals x squared plus y squared is a paraboloid, right? A parabola shaped like cup or bowl, you could say, because the traces are z equals x squared and z equals y squared. So that makes a parabola type shape in both directions and goes all the way around. All right. And so we're staying between that and then this up here, you should recognize as a cone, right? So there's a cone coming up. So we're staying in this little portion like right here. Okay. So remember in the cylindrical language that x squared plus y squared equals r squared, right? So this is going to change to r squared. And then this up here will be the square root of r squared, so it'll just be r. So I have my first integral. So r squared to r. Okay. Remember that x is worth r cosine theta. Y is worth r sine theta. And the z is just allowed to stay z. And remember, we always have to add our own r. And then we put dz, dr, and d theta. All right, so the next piece tells me, it's going to tell me my r's and my thetas. All right, so this piece right here, this was x. So is x equals 0. So if I do x and y, remember it was x equals 0. So right here, to x equals this. So remember that's a circle of radius 1. So that tells you that you're staying the right side of a circle. So, and the radius is 1. So that means I'm going to stay within the boundaries of a circle with radius 1. So 0 to 1. And then it says to do y from 0 to 1. So then that further tells me I'm going from here to here. So I'm only doing the first quadrant. So my theta is going to be from 0 to pi over 2. Okay. All right. So that took a little while to remember all that. Example 7 right here, we're going to change this to spherical coordinates. So that's a little bit more current to what we're doing now. So this is real nice right here. This is rho squared. Okay. And so when I do my problem, remember I have to add in my own rho squared sine phi. So I will have rho to the 4th sine phi. And then I have d rho, d phi, d theta. Okay. So let's figure out what the rest of this is saying. All right. So I have z equals here. So this is going to be a cone, right? And so a 45-degree cone. So I have phi is pi over 4. And I'm going up to this shape right here. So remember that was z equals that. So it's going to be the top half of a sphere, right? With a radius, the square root of 18. Right, because remember, if I work that out over here, I have z equals the square root of 18 minus x squared minus y squared. If I square both sides to see what it used to be x squared plus y squared plus z squared equals 18. If I square both sides and then move the x squared and the y squared over. So that was a sphere. So basically what's being done here, I'm staying between a cone and a sphere with radius 18. So if I think of that shape, the cone was 45 degrees, and the sphere that I'm staying between had a radius of radical 18. Okay, so that tells me to stay within a sphere, so I'm staying in that area right there. It tells me to stay within the sphere, 0 to radical 18. The phi that it tells me to stay in was 0 to pi over 4. Right? And then this portion right here, this other portion right here, if I was going to do this, remember this was x equals 0 to x equals square root of 9 minus y squared. So remember that was the right side of a circle with radius 3. So when you're solving for x, the positive side is the right side, so you were staying in that region. And then from y equals 0 to 3, the last piece right here, that means I was staying from here to here. So I was doing the first quadrant. Okay, so that tells me my theta is 0 to pi over 2. All right, now one last problem. We're just going to do this with both of these. So we're going to have to go ahead and think of our shape. So we're going to convert this to both cylindrical and spherical. So we got our xy here, so we'll remember that. Cylindrical, so I'm going to have integral 3. And remember, x is our cosine theta, y is our sine theta, and I have to put my own r with that. So I'm going to have r times r times r, so I'm going to have r to the third, cosine theta, sine theta. All right, and then I'm going to have dz, dr, d theta. We'll do the boundaries in a second. For my spherical, remember that x is rho, sine phi cosine theta, and then y is rho sine phi sine theta. So if I have x and y, I will have rho squared sine squared phi cosine and sine of theta. And I'll also add my own rho squared and sine phi. So let's put that all together. And just so you know where it could come from, I will put the answer here. So I have a rho squared and another rho squared. So I have rho to the fourth. Remember we talked about sine squared phi, but I have another sine phi on the end. So I have sine to the third phi. Then I have cosine theta and sine theta. All right, cosine theta, theta. All right, I think I got them all. D rho, d phi, d theta. Now, let's talk about the boundaries. So up here, z was staying from 0 to this right here. So remember that top one, that's the upper part of a sphere of radius 1. So we were staying, basically, if I was describing it, I would say that I was in the upper part of a sphere with the radius 1. Okay, so we have a sphere radius 1. Then the y value was staying from 0 to the square root of 1 minus x squared. So that was the upper part of a circle with radius 1. And then x was 0 to 1, so it was staying in the first quadrant right here. Alrighty, so for my cylindrical coordinates, I would change this one to be 0 to the square root of 1 minus r squared, because remember x squared plus y squared equals r squared. My r, I'm going between 0 and circle 1, and my theta is 0 to 2 pi. I'm sorry, 0 to pi over 2. First quadrant, first octant. All right, over here in spherical, my rho is staying from 0 to 1, because that's my sphere that I'm staying in. If I'm doing the top half, so the top half right here, so I'm going from a phi of 0 at the top to halfway, so pi over 2. So 0 to pi over 2. And then I am staying in the first octant, 0 to pi over 2 again. And there you have it. So remember tonight you are only doing these first problems right here. These are just description problems. They're not integrals. And the rest of this you're going to be doing in class next time. All right.